Hello, and welcome to this Eureka webinar in association with Goodfellow. My name is Paul Fanning, and I'm editor of Eureka. Today's webinar is entitled Groundbreaking Materials for Advanced Technologies, and we will be presented by Dr. Aphrodite Tomu, Technical Manager of Goodfellow. I will shortly hand over to Aphrodite, but before I do, I'd just like to remind you that if you have any questions during the webinar, please type them into the box at the right of your screen, and we will try to answer them at the end. If we don't have time for your questions, Goodfellow will try to answer them offline after the webinar. And with that, it's over to you, Aphrodite.
Hello everyone, and thank you for joining. Thank you, Paul, for your kind presentation about Goodfellow. So today we're going to discuss about groundbreaking materials for engineering applications, and my name is Dr. Aphrodite Tomu, the Technical Manager of Goodfellow. The technology to develop materials offering multiple properties carries tremendous potential for the development of applications in all industry and research sectors. Nowadays, sustainability has become a key driver to material selection. Green materials is a term used to engulf materials that adhere to the environmental sustainability principles throughout their life cycle. As such, a minimal environmental impact is ensured throughout. Their manufacturing process is materialized throughout the use of raw materials that use up natural resources to a rate allowing them to replenish. Additionally, when used as a resource for the production of new materials, they can certify their environmental friendliness, reaping commercial benefits for the manufacturer. As a consequence, green materials are attached with benefits for their users, and they result in a positive commercial and environmental impact. Thus, I have chosen to present some of our innovative, interesting, and or green materials, which can be used for renewable energy applications and other applications in general. So, in this presentation, we are going to discuss about metal materials and innovative ones, ceramics, compounds, green polymers, and as I said, sustainability is very important, innovative 2D materials, and also materials for 3D printing applications. And you are going to see how I'm joining this all. On this slide, we are demonstrating different types of metal forms, such as lost carbonate sintering forms, the traditional ones, copper oxide coated foams, and the regular one forms. These foams can be aluminium, copper metals, or other metals, even stainless steel. The lost carbonate sintering foams have smallest pores, have higher relative density, and they have high surface area. While the traditional ones have lower relative density, their cell structure is permeable with continuous ligaments, and they're characterized by high surface area to volume ratio and high strength to weight ratio. On the left of the slide, we can see the copper oxide coated foams, which are manufactured with a thin hard layer of copper oxide. This hard layer is improving their thermal performance as low heat sinks in passive cooling environments, for example, while it is enabling electronic devices to minimize their carbon footprint, which is very important. In general, application of metal forms, there are a lot, but I'll just pick some of them. So in this case, we can see metal forms that they are used as heat exchangers or energy absorbers, or they can be used also as air-roll separators, acoustic applications, filters, electrodes, etc. Specifically, metal forms having high strengths can act as high-capacity impact energy absorbers. In automotive industry, metal forms are reducing the number of parts in the car frame, and they can facilitate the assembly. Thereby, the cost can be reduced, and the performance, of course, can be improved. Due to their high surface area and their open cell structure, metal forms can be used in filtration systems and in catalysis processes. For example, a research project published in Nature Scientific Reports used our Goodfellow nickel foam in a photocatalysis experiment. The foam has been used as a scaffold template for graphene to produce a graphene foam. This 3D hybrid material shows interesting perspectives as a charge transfer materials, and that's a very innovative application, I would say. On the next one, I'm presenting some metal and alloy materials, and specifically nanoparticles. Nanoparticles are a wide class of materials that include particulate substances, which have one dimension less than 100 nanometers at least. Nanomaterials and nanoparticles are used in a broad spectrum of applications. Today, they are contained in many products and used in various technologies. There are two strategies that you can produce nanoparticles, either by mechanical crushing of source material using milling processes, or nanoparticles produced by physico-chemical processes. Our nanoparticles, Goodfellow nanoparticles, are produced via a physico-chemical process, green actually process, which enables to manufacture high purity metal or alloys nanoparticles, or even metal oxide nanoparticles with different shapes or sizes, as we can see beneath. So it can either have a needle form, or it can be spherical or cubical forms, or even irregular nanoparticles. The next slide is very busy, but I have done that intensively. Nanoparticles and nanotechnology is helping to considerably improve, even revolutionize, I would say, many technologies in the industry sectors. For example, platinum nanoparticles can be used in hydrogen fuel cells. Hydrogen fuel cells are the clean energy alternatives that use hydrogen and oxygen to generate electricity. Current platinum metal is used in electrodes for the fuel cell as a catalyst. Platinum nanoparticles, though, can improve the efficiency with an increase in the material catalytic activity and reduce the metal usage due to their high active surface area to volume ratio. This revealing an efficient and more cost-effective solution for, let's say, where hydrogen fuel cells can be used. They will be used in automotive, and we will discuss about it. Being influenced by the current situation, COVID-19, I'm going to give some bioengineering examples. So gold nanoparticles are well known to have features such as excellent optical, electronic, physical, chemical properties, and are demonstrating surface plasma resonance. For these reasons, they're used in biomedical applications. All these features that I have already mentioned can be altered by changing shape, size, or functional attached groups. As a result, they have been used in various biomedical applications such as sensors targeted with drug delivery, imaging, photothermal, and photodynamic therapy. Another example are the copper oxide nanoparticles that have been used also in many bio applications such as biodetectors, as they can display enhanced microbial activity towards pathogenic microorganisms. They have been used even in advanced sanitizers and antibacterial face masks. Other applications in general of nanoparticles include electronics, reinforced plastics, superplastic ceramics, wear-resistant and anti-corrosion coatings. They have been used for chemical sensors or technical textiles that are called smart textiles, and etc. For most ceramics, people know that they are not for most ceramics, I'm sorry, but people in general know that ceramics are very hard and brittle materials, so difficult to machine in more complex shapes. These ceramics are usually used to manufacture tiles, bricks, and pottery, and are called traditional ceramics. Example of these traditional ceramics can be clay minerals or the quartz sand, for example. The more technical ceramics, which we are going to talk about, are used in extreme environments and applications and are less frequently encountered. These ceramics have properties that make them unique, such as machinability. Yes, we can machine ceramics. So in terms of technical ceramics, machinable one is the term that we are using when the material can be turned, milled, drilled and sold without diamond tools as the traditional ceramics. And it is usually happening for the majority of ceramics, the diamond tools that we are using. One of those machinable ceramics is the Shaper high-end soft that we can see in this slide. Shaper consists of aluminum nitride and boron nitride. Except from its excellent machinability, it demonstrates high thermal conductivity, 5 times higher than alumina, and high strength while being an excellent insulator. There are several applications where Shaper can or being used as such as vacuum parts. For example, at CERN, they are using Shaper spacers in its vacuum structures. Electronic parts where high thermal conductivity is required. They are also being used for heat sinks, crucibles for vacuum deposition, and various other industrial applications. I will discuss on this slide about perovskites, which is another compound. It is a chemical compound. So perovskite materials have recently attracted significant attention as the most promising and efficient energy products for optoelectronics and photonic devices. A perovskite material has a complex crystal structure, as we can see, and as can be seen in the slide, and can be produced by combining two different cations. Perovskites are usually deposited, and they are called layer perovskites, and they are deposited as epitaxial thin films on top of other perovskites by pulsed laser deposition or molecular beam epitaxy. Thus, in our catalog range, you can find perovskites in two different forms, such as targets or sputtering targets or powders. The complexity in their structure combined with the layer structure leads to tunable properties, and that's very important. So, due to their lattice, perovskites are characterized by special properties like superconductivity, magnetoresistance, piezoelectricity, ferroelectricity, dielectric and pyroelectric behavior. In addition, a wide range of elements can be combined to form perovskite structures, providing the possibility of selective design, for example, and optimize their physical or optical or electrical characteristics. Layer perovskites can be considered as a new class of materials with confined quantum structure with huge potential for optoelectronic and electrical applications. Such as we can see on this slide, we can see that perovskites can be used in photovoltaics, electrical batteries, or as multi-layer capacitors like in fuel cells, or even next-generation display screens, memory device, and high-temperature superconductors. Everybody has discussed about, I think, or has heard about lithium-ion batteries. So we're going to discuss about this. In 1991, Sony commercialized the first lithium-ion battery, and today this chemistry has become the most promising and fastest growing on the market. Lithium-ion batteries is a family of rechargeable battery types, having several advantages over conventional lead-acid batteries. Many are used in portable devices. Compared with traditional battery technology, lithium-ion batteries charge faster, last longer, and have a higher power density for more battery life in a lighter package. A lithium-ion battery consists of a cathode, a positive electrode, as we can see on the picture on the left, an anode, negative electrode, and an electrolyte used as a conductor with a charge-discharge cycle. By simplifying how a lithium battery works, we can say that lithium ions move from the negative electrode to the positive electrode during discharge and back when charging. On this slide, we can see the compounds which can be used in a lithium-ion battery and are included in our catalog range. Each of these materials offers something different in terms of the variables associated with lithium batteries, such as energy density, high energy density, potential safety, lower cost, recharging times, cycle life, scalability, etc. Along with lithium-ion batteries offer solutions across the lithium-ion batteries offer power solution across the spectrum from energy storage solutions to portable energy solutions. Some of the most common applications of lithium-ion batteries are power backups, UPS, mobiles, laptops, and other commonly used consumer electronics goods. Renewable energy is a growing market, even in the transportation sector, and lithium batteries will play a key role on this sector too. We have discussed about the sustainability in the beginning of this presentation, and Goodfellow has launched a green production initiative materials which are the result of environmentally friendly processes that conserve energy and also natural resources. We have developed a range of materials that strike the right balance between product quality and reducing the product's carbon footprint, allowing our customers to focus on research and product design without compromising in quality. Some of these materials are presented on this slide. Cellulose acetate, for example, is derived primarily from two sources, wood pulp and cotton fibers. Applications that cellulose acetate is, for example, there are a lot, and they are on the left on this slide, and mainly it has been used in the past in photographic films. Nowadays, it is used in the automotive industry because of its mechanical strength, toughness, wear resistance, transparency, and moldability. In addition, its high resistance to impact makes it a desirable material for protective goggles, tool handles, and oil goggles. On the right of this slide, we can see the polyhydroxybutyrate biopolymer, or otherwise PHB. PHB is a polyhydroxyalkylate, or PHA, and it's a class of natural polyester that are derived from bacterial fermentation. While I would say that the polylactic acid as well involves the bacterial fermentation of renewable resources such as roots, cassava roots, or chips and starch, or corn starch, and sugarcane. Both PLA and PHB are fairly hard and brittle polymers. PLA has a low deformation and break, while neat PHB has a low melt viscosity and is brittle polymer with a higher modulus of elasticity. Because of their biodegradability and biocompatibility, both biopolymers can be used for single-use plastics such as food containers, utensils, surgical stitches, pins, packaging, and carriers, also for drug delivery. One of the most well-known nanomaterials that we are going to discuss about, and with a great impact on research and industry, are the carbon nanotubes. Carbon nanotubes are cylindrical molecules consist of rolled up sheets of single-layer carbon atoms. Their length can reach several micrometers to millimeters. Due to their chemical bond, an extra strong bond, which is called sp2 hybridism, and their molecular interaction, their structure actually, they are characterized of developing ultra-high strength while being low-weight materials with high electrical and thermal properties, as we can see from the tables presented. Carbon nanotubes have theoretical strength better than steel, while they are characterized with thermal and electrical conductivity, again theoretically higher or similar to copper, respectively. Specifically, Goodfellow owns through our portfolio beyond of powders, which is the typical form for carbon nanotubes, carpets, or I would say otherwise they are called forests. They are produced by specific chemical vapor deposition method, and which provides high pack intensity with vertical growth of carbon nanotubes. This high quality with less defects and any other commercial, this is very important because this method is producing high quality with less defects than any other commercial carbon nanotubes. Commercial carbon nanotubes carpets are supported usually on copper, while these carbon nanotubes are freestanding. The freestanding carbon nanotubes carpets can utilize their capabilities such as electrical and thermal conductivity in their full potential without being supported of copper or something else. So you can use it, for example, on your PCB devices. You may wonder how these carbon nanotubes carpets may look like. Thus, I have embedded some pictures, and you can see a macro scale picture of carbon nanotubes carpets and a cross-section microscale SCM picture of the carbon nanotubes carpets, demonstrating the nanotubes alignment. Carbon nanotubes nanocomposites are highly attractive alternatives to conventional composite materials, such as if you're using, let's say, carbon fiber composites. And that is due to their mechanical, thermal, chemical, and electrical properties, such as we said, conductivity, tensile strength, or even flame retardancy. These composites promise to offer increased wear resistance, strength, and antistatic properties, as well as weight reduction. Due to their hollow, for example, interior, they can be filled with various nanomaterials, separating and shielding from their surrounding environment. This property is extremely useful for drug delivery applications. They are also used in sporting goods, such as bicycle frames, tennis rackets, and golf clubs. Due to their antistatic property, carbon nanotubes can be used in textiles, which are called, again, as I mentioned before, called smart textiles. Being lightweight with high-strength materials, carbon nanotubes can be used in automotive and aerospace sector. It has been estimated that the aircraft weight can be decreased by 30%, and that's very important. Due to their electrical properties, as they are extremely sensitive to the effects of charge transfer, they can be used in sensors to detect, for example, gases, for example, flexible hydrogen sensors, which currently they have been used single-wall carbon nanotubes and palladium nanoparticles. Also, they can be used as, due to their electron transfer capabilities, they can be used as electrodes. Alternative to graphite, as we discussed in, for example, lithium-ion batteries. In addition, due to their electrical conductivity and their shape, carbon nanotubes can be used for field emitters displays, as they have found to have higher brightness emission at lower voltages compared to tungsten filaments that we are already using at the moment. Another class of nanomaterials similar to carbon nanotubes are the boron nitride nanotubes. Boron nitride nanotubes are lightweight and mechanically strong as carbon nanotubes. However, they are more thermally and chemically stable than carbon nanotubes. In addition, they have 200,000 times higher thermal neutron absorption capacity than the carbon nanotubes, and they are electrical insulators. This is very important for applications that we are going to see in a while. For example, boron nitride nanotubes can be used as filler in polymers, such as, let's say, polymers such as PMMA, polymethyl methacrylate, PS polystyrene, or polybutyrene as well, enhancing the heat dissipation capacity while maintaining their electrical insulation. These composite materials can be used in IT devices, such as in PCBs. Due to their high surface area, can be used in catalysis for removal of environmentally hazardous elements. For example, the conversion rate of carbon monoxide can be higher in a catalytic converter of the exhaust. They are suitable material for containers for radioactive waste, and they can be used as neutron shield and absorber material in general. Their enhanced chemical inertia favors their compatibility as well. Thus, they can be used for drug delivery systems. Goodfellow offers the unique purities of 90 and 70% purity, with the usual commercial purities being about 50 to 60%. This is another unique selling point of Goodfellow. Everybody, I think, has recently introduced to the graphene world or has recently learned or heard about graphene. Graphene has been the subject of important investigation since its isolation in 2004 from graphite at the University of Manchester, resulting to a Nobel Prize in Physics for some researchers, Andrew Game and Konstantin Novoselov, in 2010. Graphene is a disruptive technology, yes, we can say that, a wonder material, one that could open up new markets and even replace existing technologies of materials. It is one atom thick crystalline. It is a one atom thin crystalline of a form of carbon, in which carbon atoms held together by strong, very strong bonds, arranged in a two-dimensional honeycomb lattice, as we can see in the pictures. Goodfellow here is presenting the only one high purity green graphene produced by a high scalable chemical-free process. This process involves breaking methane, a potent greenhouse, as we know, which is a harmful byproduct of processes like farming, landfill, or palm oil milling, into elemental hydrogen and carbon in a plasma reactor. The process, I would say, that the graphene is formed, and the elapsed time of this process is less than 1 second, and that's very, very important because we can understand the high scalability and the quantity that we can make during this process. Goodfellow offers two types of green graphene: a predominantly one-layer graphene occurred by special heat treatment, and a few-layer graphene. The process, as we said, is green, and it doesn't involve any additives or catalysts or metal impurities, resulting to a very high purity graphene, unlikely with other commercial graphenes, which are usually containing metal impurities because they are produced, let's say, by a CVD method, where in the CVD method you are using metal catalysts. The resulting graphene is characterized by optimal electrical, thermal, and mechanical properties. The vast number of products, processes, and industries for which graphene could or even have created a significant impact stems from its amazing properties. Some of the industry applications are demonstrated in this slide. Graphene is used, for example, in an automotive components such as pumps cover, engine covers, and I would say that firstly, Ford used graphene polymer composite foam in Mustang and F-150 models, and these composites have proven to improve the mechanical properties by 20%, the heat endurance by 30%, while noise reduction has been also encountered. The important is that all these benefits came out without any penalty at the weight of the car. It is also used in aerospace, enhancing the mechanical performance of the parts while producing a lightweight material. Another application of graphene in aerospace is the use of a special graphene coating for the de-icing of the wing, of the airplane wings, and this is currently being under research and development. In construction, it is explored as a self-healing cement composite material. Also, it can be used in water desalination membranes, which are mechanically robust, and its nanoside pores, together with its reactivity towards polar or non-polar water pollutants, maximizes the water permeability while it separates particles based on size, shape, and charge. In addition, functionalized with proteins or other groups, graphene is also used in medicine as drug delivery systems. Graphene also has been used in sporting goods such as rackets and training shoes. While being a lightweight material, the training suits by Innovate, which is a company in the UK, have outlasted 1,000 miles more and is scientifically proven to show 50% better wear resistance. And last but not least, it can be used in smart textiles due to its electrical properties. We have discussed throughout this presentation for nanomaterials and their implementation to polymer matrices. As we have already mentioned, nanotechnology plays a crucial part in all industry sectors, even in 3D printing applications. 3D printing almost dominates our daily life, and it is expected to continue having a significant impact in all the industry and R&D sectors for several years. While sustainability has a great interest and challenge for all research and engineering areas, Goodfellow combines these emerging technologies and is offering two 3D filament composites. One filament is the PLA or polylactic acid enhanced with graphene, demonstrating enhanced properties such as strength, thermal conductivity, anti-static, and dimensional stability. And the other filament is the PLA enhanced with spherical nanodiamonds, offering high thermal conductivity. While the nanodiamonds though are spherical, this filler is less abrasive than other fillers that are used in general for composites in 3D printing filaments, because the other filaments in general, they have irregular shape fillers. This one, because of the filler and the spherical shape, it is leading to lower nozzle wear resistance and offering enhanced printing speed due to their lubrication properties. Concluding, I would like to mention that we have gone through a small sample of the Goodfellow's materials comprehensive range, which can be used in advanced or modern and traditional technologies. Moreover, Goodfellow offers a range of high-quality green materials supporting our customers' environmental performance enhancement. By selecting high-standard and high-end unique materials, Goodfellow is playing a critical role in facilitating engineering, innovation, and research. For any technical inquiries and other technical support, please contact us at technical@goodfellow.com. Thank you very much, and thank you for listening to this presentation.
Thank you very much, Aphrodite. We have time for a few questions here. I'd just like to start with this one. What are the advantages and disadvantages of perovskites?
All right. Advantages of perovskites. First of all, the battery production process is simple. It is oftenly produced in laboratories, for example, or in industry in the labs by phase deposition or vapor deposition processes, liquid gas, mixed deposition processes, which are very, very simple. Also, the battery power cost is low and even could be lower than a thermal power. And building, for example, perovskite, which is very, very thin, and you can produce very thin film batteries, and they can be deposited also, for example, on a glass, and you can control the thickness of each layer and the material to achieve different levels of transparency or even efficiency. And also applications might include, let's say, very lightweight batteries. However, as you have already mentioned, there are some disadvantages, unfortunately. So, perovskites are toxic materials because they're using lead, and perovskites which contain lead can have, for example, or they might also not only contain lead, they can also contain, for example, gallium, tellurium, cadmium, or arsening, and that's very, of course, hazardous. However, the Northern University has developed a substitute to thin lead perovskite solar cells, but the battery conversion efficiency is only 6%. So I will say that currently toxic materials are being used. Also, the material is not so stable because the lead in perovskite can easily make neodyne volatility, and it is easy to decompose when crystals are, let's say, wet, or there is a presence of humidity. And that's unlikely to use for, let's say, in batteries. In addition, the battery life is not long at the present, and the life expectancy of perovskite solar cells can reach up to 1,000 hours, while the battery life for the traditional, let's say, silicon ones that we're currently using generally can be about 25 years longer than a perovskite battery. However, a lot of research and a lot of development has been recently, let's say, performed or conducted by research and engineers throughout the world. So I'm sure that we are going to find a lot of these advantages in perovskites because you can tune every property of them.
Okay, thank you. Second question. What are the limitations of lithium-ion battery technology, and what other materials could be used instead?
Yes, the limitation in lithium-ion battery technologies are not so many, I wouldn't say, but lithium-ion batteries, they require protection circuit to maintain the voltage and the current within the safe limits. Also, they are subject to aging, even if not in use. They have to be stored in a cool place at 40, let's say, percent charge reduces while this aging effect if we don't store them in a cool place. Also, there are some transportation restrictions, shipment for large quantity, and regulatory controls. It is expensive to manufacture, which is not happening with the Perovskites, so that's why they're battling between the batteries and which material you're going to use. And the cost of lithium-ion battery is 40% higher than a nickel cadmium, let's say, the traditional one. And so it's not a fully mature, I would say, area, and currently metals and chemicals are changing and on a continuing basis, and researchers are developing this field as well. You have also asked about other materials that can be used. Yes, in a lithium-ion battery, materials that can be used are, for example, they can be copper foils as current collectors, nickel foils again as current collectors, cobalt or aluminum foils for the battery slurry. Also, graphite is being used for the negative electrodes. Silicon elastomers or PVDF films, they're used as binders, depending, of course, on the battery that we are going to produce.
Okay.
Thank you.
Okay. Third question. What are the limitations of nanomaterials in terms of health hazards?
Yes, there has been a lot of discussion about it, and nowadays, because the public awareness of nanotechnology is increasing rapidly, largely as a consequence of non-specifically regulated introduction of products containing nanomaterials into the marketplace, has started to be very, very important and very concerning. So, for example, self-cleaning windows are used, stain-resistant clothes, and better tennis rackets, as I said, and they're very well known. So there are health and hazardous limitations. So associations with exposure to pollution particles in, let's say, epidemiological studies have been conducted, and also transgression of biological membranes, for example. The role of the size and the shape of the nanoparticles is very important. For example, the carbon nanotubes have been classified as hazardous materials, unfortunately, beyond their capabilities. Carbon nanotubes may be long, but they are frequently curl up into turbulent balls, and due to the defects in the graphene structure and their interpretation by other carbon nanotubes, sometimes they have very low aerodynamic diameter and could reach the deposit in the deep lung and deep in the lung, and help. We should inhale them. So much debate has been surrounded, and the possibility that roughly spherical nanoparticles also may exert their toxic effects, and they can pass through epithelia and tissue membranes, and exposure to them. Anyway, the toxicity also of the manufacturing process is also encountered for, let's say, because hazardous chemicals are being used. However, in the UK, the Health and Safety Executive has recently published a guidance on safe handling of carbon nanotubes, and by using, let's say, HEPA filters. And also, one more general guidance has been provided by the British Standards Institute that has published the first extensive, I would say, guide to safe handling of all of these nanomaterials. And this was published in 2009. So we're in a good place, I would say, at the moment.
Okay. Thank you. And finally, what's new in materials science for the automotive industry?
Beyond the foam that we have already, in the metal foam that we have already discussed, And vehicles in general seek to become more efficient in their use of fuel, whether electric gas or diesel, and light alloys like aluminium and magnesium can significantly cut the weight of the motor of the engine, and also in fact, let's say a 10% reduction in vehicle weight or 7% increase in fuel efficiency if you're using alumina or magnesium at this point can be gained. Also, a lot of electronic vehicles, so we can see manufacturers are trying to introduce them into the market, so including Tesla and BMW, which they're not using anymore even the carbon fibers, but they're using light alloys, as I said before, from aluminum and magnesium. New battery technologies as well. That's why I introduced this presentation, and we discussed about lithium-ion batteries or even perovskites. So, for example, lithium-ion batteries are used already, and of course, hydrogen fuel cells will be used. And BMW has confirmed that plans to begin offering a hydrogen fuel cell version in 2022. So a lot of research is going through in the automotive industry. Also, another one I would say are the surface coatings, which enable great, let's say, management while ensuring the longevity and the reliable performance of, let's say, future batteries. So coatings are being done in batteries, for example. So they will maintain the charge and also their life cycle. Nanomaterials coatings are used throughout the industry, and they're helping to increase the performance of the ultralight alloys of aluminum, for example, or the magnesium that I said in the beginning. These coatings also can be either, let's say, anti-corrosive or wear resistant, or they can have they can be used in thermally challenging environments. And of course, I would say then glass materials or even ceramic materials. There is a great range. As I said, the most important ones and the innovations at this stage. So yeah, thank you.
Okay, thank you very much. That's all the questions we have time for at the moment. But as I said earlier, if there are questions that have been asked that we haven't been able to answer, then they can be taken offline. But for now, all that remains is for me to say thank you very much to Aphrodite, and thank you very much to you, the audience.